Last unit of trigonometry for your class, 7.3, law of cosines. So we have the standard forms of law of cosines. They look very similar to our Pythagorean theorem. However, there is a correction factor because we are not actually on a right triangle. They had to put a little correction factor in it. And I want you to notice how these formulas have this relationship of the angle and the side that you're trying to find. There's a relationship between those two things. And then if you have the alternative forms where you're trying to find the angle, there's also a relationship there. So look at how that's the minus. You can see that relationship of how that particular formula is set up. Now, when you have a choice, if you have a choice and you're doing an inverse function and you have a choice between law of sines or law of cosines, the better one to choose is law of cosines. Why is that? Law of sines has acute angles and obtuse angles. Both have positive ratios. So it's unclear when you're doing an inverse sine of the ratio. When it's positive, it's unclear where you are located. But law of cosines, which we definitely prefer, it has more clarity because positive ratios for cosine will be in quadrant 1 and negative ratios for cosine will be in quadrant 2. So that means that if you have an acute angle, your cosine ratio, when you do your inverse cosine, that ratio going in will be positive. And if you have an obtuse angle and you are doing an inverse cosine, that ratio of adjacent over hypotenuse that goes into your inverse cosine function will be negative. So that's the advantage to law of cosines, is that there will be only one angle identified by its ratio, unlike law of sines where it is unclear which angle is the correct angle. The reason why we can discount quadrant 3 and quadrant 4 is because all of those are too big to be triangles for a triangle. That's kind of low. Probably should move that up. So that's too big for a triangle. When can we use law of cosines? We need 3 pieces of the triangle. We need to have either a side, 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 or a side angle side. So, and side angle side would be that when you know 2 sides and their included angle, which is kind of helpful for finding area. But remember, area uses sine of the angle. Whatever that angle is, you're going to be using sine. So unlike law of cosines where you're solving for the triangle. Okay, page 2, we're going to draw this triangle. Home stretch. Side B, or angle B, A, C. Okay, we have 60 meters, 45 degrees, 46 meters. It looks like I don't know side B, I don't know angle A, I don't know angle C. I have a side angle side situation. Using law of cosines, I will first try to get side B. So finding side B. Oh my gosh, Billy scared me. B squared equals A squared plus C squared minus 2AC cosine B squared. or B. Sorry, had somebody visit in COVID-19 times. That's strange to happen. 60 squared plus 46 squared minus 2 times 60, 46 cosine 45 degrees, which I know is root 2 over 2. Hopefully you know that by now, but don't really need to use it. Okay, so we get B equals the square root of 1,812.77. We get 42.6 meters. We have now solved for side B, but we need to get angle A, and we also need angle C. There's possibility when I look at these sides with side A being the biggest side, 60, that's a possibility to be an obtuse angle. I think I'll go for that angle first. So cosine of A will be, now I get side B, which I have, 42.6. Of course, I'm using the really long version. I'm going to square that. Plus 46, and then minus 60 squared all over 2. And it's kind of interesting, that number comes down. That was side B. And then side C comes down 46. So notice how angle A and side A, there's that relationship. And so I get a ratio of 0.084395. Now I need to get the angle A is going to be my inverse cosine of my ratio, my opposite over hypotenuse. So the inverse of my ratio. And when I punch that in, I get 85.2 degrees. So not obtuse. Actually, I could tell it was not obtuse as soon as I saw it was a positive ratio. But that was the only side that could have been obtuse because it was the longest side. So I know all the other sides need to be smaller than 85.2. I could use my my formula to get angle C, or I could just use the principle of a triangle, 180 minus the 85.2 minus my angle. My other angle was 45, and I get 49.8 degrees, and that would be angle C. So I've found angle A, angle C, and side B. And now I'm going to get the area, and since I saw that the original problem had a side angle side, I am going to use the sides that were given to me, which happened to have been A, C, and sine of B. So using the information that was given in the problem, let's see, A is 60. Sine of 45 degrees, and that gives me 975.8 meters squared. So I've solved that triangle using law of cosines. Now I'm going to do another triangle with law of cosines, and this one definitely does have an obtuse angle, and you'd always want to go for that obtuse angle first. So let's look at this triangle and see if we can identify which one would be the obtuse angle. When we draw our triangle, and I know it's not going to be to scale, but that's okay. If you want to make it to scale, you can. But I am going to just label this triangle up. And when I label it and seeing that this is the longest side, that is the only side, the only angle that has the potential to be obtuse. So if I start with that angle as my first angle, that would be an excellent idea to do that. I'm going to start with angle A though, just because I want to point out how the law of sines doesn't work very well with angle B, because I do know that angle B is obtuse. I'm going to find angle A first just to illustrate that fact, how valuable angle the law of cosines is. And I would have gone for angle B first in a test situation, but because I'm just trying to show you this, that's why I'm going for angle A. Okay, so I'm putting my numbers in. I've got a side situation, so I am going to put my numbers into the cosine A formula. B squared plus 14 squared minus 19 squared over 2, 8, 14, giving me, whoops, that's not the right, those aren't the right numbers. Those are, messed that up. I'm not restarting this thing though. Angle A, let's see here, side B, 19. Side C, 14, minus 8 squared. That was a close one. 2, 19, 14. When I punch that in, I get 0.92669. That's cosine A. And if I want angle A, I have to do the inverse cosine of that ratio. So angle A, inverse cosine of my ratio, inverse of the 0.92669, and I get an angle of 22.1 degrees. Now let's say someone did angle A first, because A is the first letter in the alphabet, and they weren't thinking about which one was obtuse. So now that I've got my angle A, I might feel like, okay, let me use law of sines and let me get angle B with this relationship. Now if I do that, so this is not suggested here, not recommended, is I would set it up with, let's see, sine of B over 19 would equal my sine of 22.1 over 8. And when I do that, I get sine of B equals 19 sine of 22.1 degrees over 8. And then I get sine of B is equal to, and then I need my ratio, which actually I'm going to have to punch that in. Sine of 20, I might have some rounding errors because I don't have the exact, so 8, 9, 3, 5. And so my angle B, angle B, I think that it's 63.32. But was that correct? Was it 63.2 or 32 degrees? So 63.3. Or was it in quadrant 2 with a reference angle of 63.3, with my angle being the obtuse angle? Was it really 116.7 degrees? Which one was it? So this right here is not a good idea. Which is it? You don't know. That's the reason why law of cosines is much better in this kind of a situation, because law of cosines will tell us exactly which angle it is. So cosine B is equal to a squared plus b squared minus, I know I have to have B on the end because if I have my angle B, see, I'm doing all the little mistakes that people can make. If I have to have my angle B, then my B should be over there. Now let's put these numbers in. Cosine of B will be A. A is 8 squared plus C is 14 squared minus 19 squared over 2. Bring the 8 down, bring the 14 down. Cosine B equals, and my ratio is a negative 0.4508. Now you can see why that angle is indeed the obtuse angle is the correct angle. Sometimes it's the acute angle, sometimes it's the obtuse angle. Knowing the other side, because law of sines didn't involve all the sides. Knowing all the sides together gives me enough information to know that my angle B, the inverse cosine of my ratio of negative 0.4508, my angle B will be the 116. Actually, with more precise rounding, I get, let me write angle B, get 116.8. And now that I know two of my angles, I know angle A and I know angle B, I will get angle C, and I will just use my rule of, you could always use the law of cosines for this next angle, and if it comes out matches, so that when you add the three angles that you get 180, that's a great way to check yourself. So angle C we have determined to be 41.1. We have now, of all 6 pieces of our triangle, the 3 sides, the 3 angles, we have solved the triangle. Last step to do is solve for our area. And I think the best thing to do would, well, there's no best. I guess angle C is on my calculator right now. So I'm just going to use that one since it's on my calculator, but I could use any 2 sides and their included angles. So if I want to use angle C, I'll go with 1/2 8 times 19 times the sine of 41.1 degrees. But really any of these combinations is the same. You want to use the 8 and the 14. Make sure you use the sine of that 116.8 degree angle. If you want to use the 14 and the 19, I really don't care, but you have to use the 22.1 degree angle that's formed in the middle, because all of these areas will come out the same. Notice how they use sine, and all the areas came out to be approximately 50.0 feet squared. Any one of those that you pick. Now to do a little bit more complicated problems, some word problem type things, and just to show how law of cosines is something really important for navigation and also surveying. Okay, so the diagonals of a parallelogram, so using some word problems. Let's draw what this is saying. We have a parallelogram. Draw that nice and big. And it says that, and so just to show with some markings that those sides are parallel to each other. And they say that they have diagonals through this parallelogram. And what's interesting about that is that parallelograms, actually, their diagonals will bisect each other. So we know that these are going to be congruent with each other. And they have the shorter diagonal is 24.2 centimeters, and the longer diagonal is 35.4 centimeters. There is an intersecting angle of the smaller angle, and it's hard to tell which one is smaller, but I think this one looks a little bit smaller, so 65.5 degrees. And I know that the other angle will be supplementary to that angle. That angle, if I was interested in it, would be, let's see here, would be 114.5 degrees. So if I needed that angle, I could use that angle as supplementary. And vertical angles, those angles will be congruent. The 114 will be congruent with its vertical angle. Those are properties that help us use law of, or figure out the pieces of this triangle to find a triangle within this situation. So I see a triangle right here. It looks like a very nice triangle. What information do I know about this triangle? Let's redraw the triangle out here. We know that this angle, being a vertical angle, is 65.5. We know that the diagonals will be bisected, so each segment that it's broken into, 17.7 centimeters. Let me write that down here on my, this is 17.7. I'm going to write it on my triangle. And then I have my other diagonal being bisected, I get 12.1. So that is 12.1, and I will write it on my triangle, which I like to write my triangles out to the side, and I'm looking for side X. That's going to be the shortest side because the side opposite of the 114.5 degree angle will be bigger than the side that's across from the 65.5 degree angle. So if it helps you, you can label your points. And so it looks like I'm going to be using the B relationship. So let's just say that I'm going to be using B. So I would say B squared equals A squared plus C squared minus 2AC cosine B. And that gives me my X. Okay, side A, 12.1 squared plus 17.7 squared minus 2, 12.1, 17.7 cosine 65.5 degrees. And that gives me, I'm just going to punch it into the calculator just to show you how to punch something like that into the calculator, because if anybody's having trouble with this section, it's usually about how to punch things into the calculator. So let me find my calculator. Let's see here. Where's my calculator? Right here. Okay, so if I'm punching up let's clear that. Okay, so 12.1 squared, I'm going to punch it in as one long piece minus 2 times 12 point. Notice I did not hit return. I am still typing my formula, and I am in degree mode, which I already had checked, and I get 282.1 roughly. And when I take the square root of that, and you could use the square root key, second x squared, but I'll just raise it to the 0.5, which is also taking the square root, and I get 16.79 as that side. So 282.1, that would be, and then I take the square root, and I get 16.8 centimeters as the shorter side of my parallelogram. Now about practical applications of law of cosines would be in navigation as well as surveying, and of course they also use law of sines as well in there. But we're going to just show you what it means to have navigation, what a heading means. Headings are when you measure you would go clockwise from due north. So unlike in our Cartesian coordinate plane where we were rotating counterclockwise, in this situation, north arrow, we'd have our compass out and we'd rotate clockwise from our north arrow. So the true course of an object is the angle measured clockwise from due north to the vector representing the actual path of the object. Vectors means that it has direction as well as, magnitude. So here is if we were drawing a course of 50 degrees, I would measure off of 50 degrees, or off of north, and just draw this so I can sort of get an idea. Okay, it'd be about like that. That would be a course of 50 degrees from the north arrow. And if I was going a heading of 90 degrees off of my north arrow, I would be actually going directly east, wouldn't I? That would be a 90-degree course, would be going east, but they would call it 90 degrees. And then if I had a heading of 268, I would go past 90, past 180, but not quite to 270. It's a little strange having 270 be over there, but that is a course of 268.2 degrees. So how do they do this in navigation? Let's have our ship. Here's our nice little ship. Well, let's have him head out on a heading of 60 degrees. So here he is, starting here. Here's our north arrow. Starting here, he's going off of my north arrow, 60 degrees. So there's my ship right here. There's the boat heading out for a distance of 5 miles. And they were at 60 degrees for 5 miles. And then at some point, the ship stops and the captain says, let's turn ourselves to a heading of 160. Turn yourselves to a heading of 160 and continue on, little ship. And then the captain says, wait, where are we now? We just drove or sailed 3 miles. How far did your ship travel from the original spot where our boat was originally? So we're going to have to use parallel lines, alternate interior angles. Like, for example, if we have 2 parallel lines, these angles, these alternate interior angles will be congruent. These alternate interior angles will be congruent. So when I look at my line, if I pretend like this is a blue line for a second here, you can see that this north arrow is parallel to the other north arrow. And so my alternate interior angles, which would be congruent, would be those right there. So this angle right here is actually 60 degrees. But that doesn't help me with this little piece of angle on this side. But if I remember that this is 160 degrees, this little angle must be 20. That gives me enough information to find my side X. X squared will be, and if it helps you to label with A, B, and C, definitely do so, but 5 squared plus 3 squared minus 2 times 5 times 3 cosine 80. X squared will equal, let's see, minus 80, I get 28.7906 square root x equals 5.4 miles. I'm just rounding it. And so I'd say, hey, Captain, we're 5.4 miles from where we started. So this is a kind of complicated example. It involves a little bit of law of sines, but we have a plane that's flying at an airspeed of 170 miles per hour, but we know that the wind is going to push on this plane. And so when the plane is setting out on a heading of 52.5, we need to first start by drawing the plane on its course, and then we're going to examine what will happen as this wind is pushing on our plane. The wind can help our plane and the wind can hurt our plane. Sometimes the wind helps you fly faster. Sometimes the wind will make your plane go slower because it's pushing against it. You've walked or run into the wind, and that's, let's put this point B, and we know that our plane was flying at 170 miles per hour. And we have, so now there's our plane trying to fly at 170 miles per hour, trying to fly at a course of 52.5 degrees. Here's my other north arrow whenever my plane stops. But in fact, we realize that our plane is not flying at 52.5. The plane, she, he, whatever, is really flying at 64.1. So let's draw a different line, and this other angle is 64.1, and 64.1 subtract the 52.5 tells me that the little sliver of an angle here is 11.6 degrees. And so our plane is actually flying on that, and we don't really know how fast our plane is flying. That's the question. How fast is it flying as the wind pushes on our plane, or pushes behind our plane, helping us along? Which way is it going? So if you think of the wind currents are at 40 miles per hour, if our wind current is pushing against our plane, think of that point B with a radius equal to 40 miles per hour. As I swing my arc, I could have a wind of 40 miles per hour that's pushing against my plane, making my plane slower. Or I could have a current that's pushing with my plane, and it will be making my plane faster. And that's the jet currents that as you fly in a plane, sometimes your plane goes faster than you expected, and it's because the wind's helping you, or slower than you expected. So we have two different triangles, and we're going to try to solve these triangles, and it looks like I have a side angle situation for my triangles. And I'm going to have to look for angle, let's see, I didn't label it, but why don't we label, let's see what we can find. Let's draw our two triangles. Let's see what we would find. 40, 170. So we labeled that. I'm going to call this C down here. So there's one of my triangles. And then that was the smaller, well, I guess the obtuse at C triangle, acute at B. But here's the obtuse at B and acute at C. That's this. This is where you're going faster. So it looks like from law of sines, I can go for angle C. And in both triangles, they look kind of like the same exact setup. So let's set it up. Sine of C over 170 will equal sine of A. Whoops, I know what A is. Over 40. So let's see, sine of C will equal 170 sine of 11.6 degrees over 40. Sine of C is equal to a ratio of, let's see what it is, the ratio of 0.85458. So now we have to get our angle C. Looking at our two triangles, you can see that this triangle on the right is actually the acute quadrant 1 angle for C. And we'll find out what that is. And on the other triangle, that is our obtuse quadrant 2 angle C. So let's find out what those two numbers are. When I do my inverse, sine, I get an angle C of 58.7 degrees. So that is clearly for the, that's clearly up here on the right triangle, 58.7 degrees. And as I put that angle, my reference angle of 58.7 into quadrant 2, I can get my obtuse angle for angle C of 121.3 degrees. So let's put that over here. And now I can find my angle B for each of these triangles. I can find my angle B. So angle B in triangle on the left, looking at the principle of being 180 degrees, is 47.1. Angle on the other triangle, keeping it clear, 109.7 degrees. And then I could find my speed on the cross from there, using that law of cosines. I could set that up. And so let's see here. I'm just going to set up one of them. I think I'll set up the one on the left just for the heck of it. Whoops, I need to see what angle B is. Okay, so I've got the two sides. So x squared will equal 170 squared plus 40 squared minus 2 times 170 times 40 times cosine of 47.1 degrees. And when I do the square root of x squared, I get a speed of 146 miles per hour. That is the slower speed. And when I set up the other one, I get x squared equals 170. Let's see here, 170 still is 40. Okay, different angle. 170 squared plus 40 squared is 2 times 170. But this time my angle is now a different angle. It's 109.7 degrees. And when I do that angle where this plane is being helped by the wind, I get an airspeed of 187 miles per hour, which is faster than we even expected to be going. So the last page of notes, last notes of trigonometry, and you're all done. Just have to do the assignments. Here's a quick summary of when to use the different versions, and I have a little star next to the law of sines because that is the ambiguous case. And whenever possible, Please use the law of cosines because it doesn't have the issue of the second quadrant being another positive angle.